In this section, we're going to look at tangent and normals to curves. And we'll start with a short revision of the straight line. There are two basic forms of the straight line. One is the general form, the line being described as ax plus by plus c equals 0. And the other one, much more common, is the gradient intercept form y equals mx plus q, which corresponds also to a linear function. And here, geometrically, m here is the gradient of the function and q is the y-intercept of the line, actually, rather than of the function. So we have here the line. The y-intercept means this size here where it cuts the y-axis, and the gradient is defined as delta y divided by delta x here. Yes, exactly, the gradient or slope of the line. Now let us introduce a new form where we are given a point on the line, this point A with coordinates xa and ya, and we're also given the gradient m of the line. We call this the gradient point form. Any point P on this line, as we said, given by this point and its gradient, has to fulfill the following: y minus ya, this is the delta y, divided by x minus xa. So this delta y divided by delta x calculated using the point P, this arbitrary point P on the line and the given point A of the line. Well, this ratio has to be exactly the gradient of the line. So every point on the line fulfills exactly this equation, and any point not on the line will not fulfill it. So this is another way of describing a straight line. Since we're going to look at normals, we are also interested in looking at perpendicular lines. We're given two lines, L1 and L2, and we assume that they are perpendicular. What does this mean? Well, it doesn't mean anything about their y-intercepts. However, about their gradients, we know if they are perpendicular, this means exactly that m1 times m2 is equal to -1. And if m1 times m2 equals -1, then we know the two lines are perpendicular. There is one exception if we have a horizontal and a vertical line, because then we can't write the lines, the vertical line, we can't write it in that form. But for all other cases, this is true. Try to solve example 1 on your own. Here comes the solution. We start with the gradient intercept form of a line, y equals mx plus q. Then we know m is 1/2, so we substitute it in here. And then we know the point A lies on the line, so its coordinates fulfill the equation. We insert the coordinates 5 and 4 here. We can solve that for q equals 3. And now we insert for q the 3 here, and we get the equation of the line. Now let us find the line using the gradient point form. So m equals y minus ya divided by x minus xa. Well, m is given, is 1/2, and a is also given, so we insert for ya the 5 and for xa the 4, and we've got the line in the gradient point form. If we want, we can transform it, so we get it in the gradient intercept form. We multiply by x minus 4, and then we just add 5, and we get obviously the same equation as before. Now solve example 2, practicing with perpendicular lines. Stop the film, and here comes the solution. Since two lines L2 and L1 are perpendicular, we know that the product of their gradients is -1. The gradient of line L1 is 1/2, so we have ml2 times 1/2 is -1, multiplying by 2, we get ml2 is -2. So we get y equals -2x plus the y-intercept, and the y-intercept is given as 6, so we get this final result. Note that the y-intercept of line 1 is absolutely irrelevant, because the only information we get from line 1 is that it is perpendicular to line 2, so it does not matter where it is located, whether it is here or here or here. Now let us look at the task of finding a tangent to a curve in the point with x-coordinate xa here. This means a tangent is a straight line, so we have the answer to y equals mtx plus qt, and the gradient mt of the tangent corresponds to the gradient of the curve in the point with x-coordinate xa, which means the mt, this gradient of t, corresponds to f dash of xa. And additionally, we know that the point A, which has the coordinates xa and ya is just f of xa, since the point lies on the graph of f, well, this point lies on the tangent. So we have actually, if the function f is given, and we are looking at a specific x value, for example at x equals 7, we're looking for the tangent, we can find f dash of 7, so we have the gradient, and we can find the point 7 and f of 7, and we know we have a point on the tangent. That's all that we need to find the equation of the tangent. Very similarly, we can find the normal. The normal is a straight line, so we use again the ansatz y equals mnx plus qn, and we know now that mn, this gradient, since the normal is perpendicular to the tangent, mn times mt has to be -1, and as we saw before, mn times mt is the same like mn times, now mt is just f dash of xa. And again, the point a, xa, f of xa lies on the line, on the normal, so it's element of n. So again, if we're looking for the normal in a specific point, for a specific x-coordinate, we can just find the gradient of the curve there. Then we, using this formula here, we get immediately the gradient of the normal, and knowing this point is lying on the normal, we have a point, so we have gradient and point. That's all we need to find the equation. Let us now solve example 3. We're given a function here, and we want to find the tangent and the normal at x equals 2. So what we will need, obviously, is the gradient of this function. So we have to find the derivative, y dash, which is just 1/4 times x to the power of 3 minus 3/2. The 1/4 here is just 4 divided by 16. We have to do 1/16 times 4x to the power of 3. So what we want to know now is actually the gradient at x equals 2. So we want y dash at 2. Inserting that, we get 1/4 times 2 to the power of 3 minus 3/2, which is then 1/4 times 8 is 2 minus 3/2. So we get the gradient at x equals 2 is 1/2. Additionally, we need this point A, where the tangent, or afterwards also the normal, touch or cut the curve, which means this is A2 and YA. Well, to find YA, we just insert the 2 into the original equation of the graph of the function. So we get this here, just inserting the 2 here, and this simplifies to 1 minus 3 plus 1, so we get -1. So the point A, where the tangent touches or the normal cuts the curve, is 2 minus 1. Now let us find the tangent using the gradient point form. This means mt is then just y minus ya divided by x minus xa. Well, mt is just y dash of 2, so it's 1/2. So we get 1/2 is equal to y minus 1, so plus 1 divided by x minus 2. We can transform that now if we want to get it in gradient intercept form by multiplying with x minus 2. Then we get on the right hand side still y plus 1. Left we have 1/2 times x minus 2. And then subtracting minus 1, switching sides, we get that the equation of the tangent is y equals 1/2 x minus 2. Alternatively, we could have worked directly with the gradient intercept form, so just saying y equals mt times x plus qt. Well, mt as calculated up here is 1/2, so we get y equals 1/2 x plus qt, and then we could insert a lying on t, so we would get minus 1 equals 1/2 times 2 plus q, which yields q equals minus 2, and we get again the same result. Y for the tangent, y equals 1/2 x minus 2 by inserting the q, the minus 1, 2 here into this one. Now let us look at the normal, and let us proceed the same way. Let's first use the gradient point form, and then let's look also how we could do it with the gradient intercept form. Try it on your own, and here comes the result. The gradient point form is mn equals y minus ya divided by x minus xa. We know that the gradient of the normal times the gradient of the function mn times y dash of at the point 2 is equal to minus 1. So inserting the y dash of 2 that we calculated further up here, the 1/2, we get mn times 1/2 is minus 1, and so we find mn is minus 2. Now we insert that. We insert the minus 2 here into this one, so we get minus 2 equals to y, and the ya now is still the same point like before, the point here. So ya is minus 1, y minus minus 1 is y plus 1. X coordinate still the same, so I get x minus 2 here, and solving that we get in the end y equals minus 2x plus 3 as the equation of the normal line. We can also solve that using, instead of the gradient point form, the gradient intercept form, and we get this solution here. Okay, let's look now at example 4. Try to solve that on your own. Stop the film. And here comes a first hint. Well, actually all that we're looking for is the x values for which the gradient of the curve is minus 3. So try that now on your own, and here comes the result. We find the derivative of this polynomial here, and then we know we want this derivative to be equal to minus 3. So now we need to solve this equation. By adding 3, we put everything on one side, and now we should realize we have a biquadratic equation, or in other words, we can just do the substitution z equals x squared, and we get now a quadratic equation, z squared minus 5z plus 4 equals 0, which we can solve. We get this product, and so we get z1 is 1 and z2 is 4. We're interested, however, in the x, so what we have to do is substitute back the z by x squared here. So we get x squared equals 1. Taking the root, we get two solutions for the x, plus and minus 1, and also for the z2 equals 4, we get two solutions in the end for the x, plus and minus 2. So those are the 4 x coordinates at which the tangent to the curve has gradient -3. We should find one of the tangent equations, so let's look for the tangent 1, which should be the one that touches the curve at x equals 1. Well, the equation is just y equals mx plus q. The m we know because we are looking only for points with gradient -3, so it is y equals -3x plus q. The point A where it touches has the x-coordinate 1, and we can insert now this x-coordinate 1 in here, and we find that y1 is -112/15, so this point is lying on the tangent, so we insert a into this tangent t1, and we get this equation here, and solving that for q, we find this value for q, and now we can insert it back in here, and we get the final result for this one tangent y equals -3x -67/15. Here in example 5, we have symbolized a mountain. Here we have an airplane, and the airplane is flying in a straight line above the mountain, and the question is, what is the minimum angle of elevation needed so that the airplane does not crash into the mountain? So what we're actually looking for is the tangent from this point P to this curve F, and then once we have the tangent, we need to find this elevation angle alpha. And just to remind you, well, this is the arctangent of the gradient of the tangent. Why is this the case? Well, when we take here the this triangle, we have a right angled triangle here, and this divided by this is the gradient, and that corresponds exactly to the tangent of alpha. Let us call the point where actually the tangent touches the function point A, and this has the x-coordinate xa, and correspondingly the y-coordinate is then just f of xa. So our task is to find the tangent t to the curve f through the point P. Well, to find the tangent, we know we'll need the derivative. The derivative is f dash of x, so we get -1/5 x plus 2/5. The tangent is a straight line, so we could write it in gradient intercept form, y equals mx plus q, but it turns out that it is a lot simpler to use the gradient point form, so m equals y minus ya divided by x minus xa. Now let us remember the m of the tangent is just the derivative of the function f in the touching point a, so f dash of xa, which is -1/5 xa plus 2/5 by inserting xa here for the x. And then let us find the coordinates of the point a, the touching point, which is just x-coordinate is xa, and inserting the xa in the function equation here, we get this for the y-coordinate. So inserting now all this that we have found into this equation here, we get finally this equation here. And now let us simplify it by multiplying both sides with 10 times x minus xa. So the x minus xa will disappear here, and the whole thing simplifies into this equation here. So now we have not yet used the information that the point P, the current position of the plane, lies on the tangent. So let's use that as well. This means the point 13,1 lies on the tangent. So we insert 13 for the x and 1 for the y. So here's 13, and here for the y, the 1. Now we can transform that, simplify it, and we get xa squared minus 26xa plus 88 equals 0. Using factorization, we see we get this here, xa minus 4 times xa minus 22 equals 0. And so we get two results, xa1 equals 4 and xa2 equals 22. By having a short look at the sketch up here, we see that the solution that we're looking for is here, the xa equals 4, because at 22 we would be somewhere down here. Well, that's below the ground level. That's not where we want to fly above the mountain, or whatever we want to call it. Obviously, that's the one solution we're looking for, so let's continue with that one. This means we need to find the equation of the tangent, or actually all we need is the gradient of the equation of the gradient of the tangent, which is, as we said before, f dash of xa. So we can now insert the 4, f dash of 4, and we had that. It's minus 1/5 times 4 plus 2/5, and we see it is minus 2/5. As we said just before, the elevation angle alpha, its tangent, corresponds then exactly to the gradient, which means the elevation angle we're looking for is the arctan of the gradient, so the arctan of the 2/5. It is not important whether the line here is ascending or descending, or it's like this. In the end, we want just this positive angle here, and using the calculator, we get that this angle is approximately 21.8 degrees. At last now, example 6, we're given a curve f, y equals ax to the power 4 plus bx to the power 3, and so on. So we have two unknown coefficients or parameters of this curve f, and what we know is we're given the normal to the curve at x equals 3, namely it has this equation. Task is we want to find a and b. Think about it for a moment, try it on your own, stop the film, and here comes the solution. We need to know the gradient of the function, so we need to find its derivative, and now we know that the gradient of the curve f at x equals 3, well, we know here this line here, y equals 1/2 x plus this part here, is normal to the curve. So we know, since the gradient here corresponds to the tangent there, and the tangent is normal to the normal line, so the product of the coefficient of the gradients has to be -1. So we know the product mn times the derivative of the function at x equals 3 is -1. Mn is 1/2, and f dash of 3 is 4a times 3 to the power of 3 plus 3b times 3 squared minus 2 times 3 plus 4, and that equals to -1. Multiplying both sides by 2 and expanding the expressions, we get this equation, and adding 2 on both sides, this simplifies to this equation here, and we'll call that equation 1. We have not yet used that we know where the normal cuts the curve f, which means we know it cuts it at x equals 3. Since this cutting point A is part or lies on this normal line n, we can just insert it into the equation of n. So this cutting point A has x coordinate 3, ya is unknown, it lies on n. We insert in here ya, and then the 3 for the x, and we find ya is minus 9, so we found this cutting point is 3 minus 9, and this point lies obviously on the curve f, so we insert that one now into this equation here, and we get this equation here, and again this simplifies by subtracting minus 27 halves and plus 9, and we get this equation here and this here. Now what we'll do, we'll take this equation, this equation 2, and subtract it from 1. So we'll do 1 minus 2, and here we have the 1, here we have the 2, so 1 minus 2, 27a remain, the 27b here, they get cancelled out. Here we have 0, so on the right hand side what remains is just the 27 halves, and dividing by 27 we get a is 1/2. Then we can just insert that in one of the equations. Let us insert it into equation 1 here. So we have 108 times 1/2 plus the 27b. So we get here 54 equals minus 27b, and the final result is b equals minus 2, and we found a and b.